Humans have done a great thing by inventing nutrient use to produce food. It has helped feed billions of people over time. The Haber-Bosch process, which was the industrial scale production of ammonium, revolutionized agriculture, but some people argue that ammonium was also used for making bombs, which has killed more people. Well, nonetheless, this is on nutrient management, which results at number 65 by 2050 and is expected to save 1.81 gigatons in CO2. So it's mostly about avoiding the use of something, and which should lead to reduction of N2O from agriculture. But there are other impacts. Human perturbation of the nitrogen cycle, the natural nitrogen cycle, is pretty serious and massive and extensive. Here the data is too variable to be determined in terms of the cost of implementation, but if nutrient management is appropriately implemented, we'll still have $102.3 billion in savings. This is one of the critical aspects when the agricultural production uses various nutrients. They change the nutrient ratios of the waters that wash into the ocean, the streams, the estuaries, the bays, lakes, and so on. So the nitrogen to phosphorus ratio is critical for natural ecosystem functioning in these water bodies, but as you can see from this algal bloom off the coast of Sweden in the Baltic Sea, you often get what are called harmful algal blooms. They produce various levels of toxins that are harmful to humans, or they end up creating fish kills, and these blooms can then die and fall down and get digested by aerobic bacteria, which leads to what are called anoxia and hypoxia. So the dissolved oxygen in the water falls to levels where fish have to either move away, or if they can't move far enough or fast enough, they can end up dying. And there are, of course, many natural sites of hypoxia and anoxia. So here is low oxygen zones from the IOC group showing 2 milligram per liter of oxygen or less, which is considered hypoxia. Less than 5 milligrams per liter is anoxia. So very few things can live in these very low oxygen waters. This is not at the surface. This is down at almost maybe a kilometer or so. So this is in the open ocean. These are natural. They are related to circulation, but the question is, how are they being affected by the warming that is related to greenhouse gas increases and human activities that lead to nutrient runoff into the coastal regions? But all these coastal regions have increasing anoxia, either in terms of the drop in oxygen levels or expansion of the low oxygen waters. So for example, Gulf of Mexico has annual hypoxia showing up because of the rainy season, snow melt, and the waters coming down the Mississippi River and so on. But human activities, and this is the breadbasket of of the US, for example, the Mississippi watershed going all the way up into the Canadian border, and all those nutrients wash into the Gulf of Mexico, and the hypoxic region is expanding. Similarly here in Europe, in the Mediterranean seas, off of China, Japan, and so on and so forth. There are some interesting numbers to look at. So if we look at world population with and without synthetic nitrogen fertilizers from 1900 onwards, these are estimates, of course. That's how the world population has grown. Now we are well over 7 billion. The world population supported without synthetic fertilizer is about half, and about half the population relies on synthetic fertilizers for the food they consume. Okay, so it's not a bad thing, it's a good thing. Like plastic, it's a miracle substance, but of course uncontrolled it's going to do a lot of damage, as has already been logged, understood, but also will continue to do so. Fertilizer use per hectare of cropland in 2015 is listed here in terms of kilograms per hectare. So you can see that there are countries which are using some amounts. China is very big on this number, greater than somewhere between 1,000 and 2,000 kilograms per hectare, and these fertilizer products include nitrogenous, potash and phosphate products, so including ground rock phosphate and so on. So in general, there is a relation between GDP and the use of fertilizers. So nitrogen fertilizer use per hectare of cropland in 2017. So you can look at potassium and potash as well. So you can see that overall fertilizer use is low here, but when you compare nitrogen, then all these countries are very high in terms of 250 to 500 kilograms of total nutrients per hectare of cropland. So this has become very normal now to just use fertilizers, just like when we talked about doing flood irrigation for rice. Even though the system for rice intensification may reduce water use and even increase yield, it's very hard to get farmers away from the practice where they rely on flooding as something they know, something they trust, something they know, think that will work, and so they're not eager to experiment on that. This is the total fertilizer production by nutrient around the world from 1961 to 2014. So this is in tons per year, and you can see that whether you look at potash, phosphate or nitrogen, they have all steadily increased, and there was a of course nitrogen is the biggest of the fertilizer, the largest of the fertilizer amount that is used. So nitrogen cycle is heavily disturbed, but the N to P ratios of waters running into the coastal regions, lakes and groundwater have also increased. So nutrient loading and eutrophication are very common problems associated with that hypoxia that we used. This is an interesting number here, looking at cereal yields in tons per hectare and amount of nitrogen fertilizer use. And you can see that for a large range of fertilizer application here, there is really not that much increase in the yield, and yet there is a tendency to use high amounts of nitrate per acre. So you can see Armenia is out here producing only 2 tons of cereal yield with such a high nitrate application. And of course there are countries here, outliers, with very high production crop yield in cereals, so that has to be understood. But there are countries which are good at nutrient management. It's not just how much you apply, but how do you control the runoff and the pollution resulting from that. That is also very important. But nonetheless, the application of fertilizer is not always based on increasing crop yield, but just thinking it's a good thing to apply anyway, especially when there are subsidies for buying fertilizers and so on. Or farmers also make loans and get trapped into all kinds of problems in some developing countries. This is something I took from Penn State University's extension on agriculture, which lists a number of things needed for a basic nutrient management plan. And I wanted to list it just to show how difficult it is to regulate and implement nutrient control. So it has to rely a lot on farmers and their awareness and their willingness to reduce fertilizer applications and manage nutrients in various integrated ways. So an inventory of nutrient sources on the farm, including manure and crop residues, not very easy to do. Nutrient analysis of each of these sources. The compositions of many of these sources may vary considerably, so book values may be inadequate for planning purposes. Just measuring and tracking these sources and sinks is going to be nightmare. Handling and storage procedures for minimizing the potential for nutrient loss around the barnyard. Going down here, nutrient balances for each field to indicate any additional nutrient needs for the crop and or any excesses that might be of concern. Plans for dealing with any excess manure produced on the farm. And so on. So ultimately, while all manure nutrient management plans should contain these basic plan elements, the actual plans themselves will take on many forms. So the idea of smart agriculture and so on are trying to do these things, but it is a very data intensive, instrument intensive process, and it's very easy for farmers to not bother with them at all. But nonetheless, the impacts will be to reduce by reducing fertilizer overuse on a total of 2.1 billion acres of farmland by 2050, up from an estimated 177 million acres currently. So that's massive increase in reducing fertilizer overuse. Avoided nitrous oxide emissions could equal 1.8 gigatons of carbon dioxide. This is the key aspect of nutrient management, is to avoid nitrous oxide emissions. So that's converted to equivalent carbon dioxide, as we did in methane as well. No investment is required, and farmers could save 102 billion from reduced fertilizer costs. And yet, how to incentivize farmers to reduce fertilizer application is not an easy problem. Our analysis assumes adoption that roughly parallels conservation agriculture, as farmers are likely to be amenable to both practices. So you have to take the integrated approach of conservation agriculture and nutrient management and reduced fertilizer costs. So even though it says no investment is required, a plan like this obviously will require investments in monitoring and tracking nutrients, and that's not zero investment. Okay, nonetheless, a no regret solution, and very important for soil health as well, and eventually to not just reducing emissions but increasing yields and reducing harmful algal blooms, infestation of fish with various